Hello and welcome to our video on topic 6. We've had our discussion and our introduction to the basic t-test, and now we're going to do part B, where we are going to work through a couple of examples by hand and illustrate how they're done in the basic way. As always, we're using our Statistics for Psychology book. Doesn't matter what discipline you're most interested in, the ideas behind these statistical tests and concepts are all the same, and this book explains them better than any book I have seen. We're going to page 266, and we are looking for number 13 here. Let's read it first. In each of the following studies, a single sample's mean is being compared to a population with a known mean but an unknown variance. For each study, decide whether the result is significant. Essentially, we're doing the hypothesis testing procedure, and we'll highlight that without a diagram, although we could draw a diagram as well. Just run through the hypothesis test so we understand what we're doing. But this is a shortened question, just giving me the facts, not the whole story. So we'll do part A and B. So let's do here, what was this? 13. A couple of questions. You see here the A1 gives me a sample size of 16. We have a population mean of 100.31. The calculations aren't shown. They've estimated the standard deviation at 2. Of course, the observed sample mean is 100.98. We are examining the right-tailed, a high predicted change. We just don't know if it's significant at an alpha of 5%. So to not forget, let's run through the basic idea of the hypothesis testing behind this. So we are testing to see if the mu, let's do the research hypothesis first. We're testing to see if the true mean is greater than this 100.31, maybe after some treatment or some effect we're investigating. And our null hypothesis, of course, is that there is no change. The comparison distribution is, like before, the distribution of means, which has our mu m the same as mu under the null hypothesis, so 100.31, and our approximate standard deviation is now going to be S to indicate that we're approximating it, not sigma, the true population mean. We don't know it. S is 2, the sample standard deviation, but adjusted to the distribution of means, as we always do for a sample greater than 1, is to take the sample standard deviation and adjust it by dividing by the square root of the sample size. In this case, we have a nice sample size, so this is a convenient calculation. 2 over 4 is 0.5. Otherwise, go to your calculator and calculate whatever it may be. So I'm following the basic steps of the hypothesis testing procedure as outlined in that textbook. We have an alpha of 5% or 0.05, depending on which version of the same thing you are looking for. Our degrees of freedom is one less than the sample size, and in this case is 15, and we need that because depending on the sample size, the t distribution that we're using whenever we have to approximate the standard deviation from the sample, it is slightly different depending on how large the sample is. Larger samples, then it starts drifting towards the normal distribution, but for samples below 100, it the tail is a bit different, and it's technically a different distribution. So let's visualize this to just make sure we understand what's going on with a little diagram, maybe here on the right. I still think about the normal bell curve shape, to be perfectly honest. It's very similar, it's just a little bigger tail. So we have here our 100.31, our mu, and we are looking at, maybe a vertical line would be good here, some cutoff that would produce 5% in the tail. What is that cutoff? We'll call it T cutoff, because this is a T distribution as soon as I have to approximate the standard deviation. So I go to my T distribution table. Looks very similar, but because every degree of freedom has a different distribution, not all of the table is given, only the highlights according to what I most commonly use, alpha of 10%, 5%, and 1%. We are in this degree of freedom 15, and we're looking for the right tail at 5%, or the tail, only on one side. One tail test, 1.753. 1.753, that'll be our T cutoff, matching the alpha. So that is what I look up. Everything in terms of the flow of the hypothesis testing procedure is pretty much the same. So that's our cutoff. Now our observed T score, we'll call it T observed. Let's go to a formula sheet here from the book just to see where we're at. We didn't have to do formula 7.1 because it was calculated for me. We did use formula 7.5 to make the adjustment to the distribution of means and estimate the standard deviation of that distribution based on the standard deviation of the sample. Now we're over here in formula 7.7, calculating the t-score as the sample mean minus the mu over the standard deviation. Very similar to the z-score calculation, right? It's just it's technically different because the standard deviation is approximated, but that is very minor in terms of the look of the formula. Now we have our sample mean, which is 100.98. 100.98 minus the mean of 100.31 under the null hypothesis, divided by the standard deviation approximation of 0.5, and we get, the whole point here is that we don't know, that difference looks very small, but it really depends on all the other aspects of the distribution to decide how small is too small. 100.98 to make a conclusion, I mean, minus 100.31 divided by 0.5 there. Calculator shows 1.34 1.34, let's write that down. 1.34. So now I'm going to compare my observed score in terms of the t-score is, let's say, sitting over here. Let's just put that a little lower here. 1.34 t observed. And of course, we standardized it in order to use the table, right? We saw last time with our power example, we can convert these to raw scores as well. So we see that our t observed is in this case less than the cutoff, and therefore we interpret the sample as not providing strong enough evidence to suggest that our null hypothesis is not true, and our conclusion therefore is to not reject the null hypothesis. Might still be false. There could be a little change in the mean. Our evidence just didn't suggest that this is the case. It wasn't strong enough to make that conclusion based on the probability of us making a mistake, 5% that we're okay with. All right, so very similar in terms of the look and the steps and everything. The only difference is we have an approximate standard deviation and then technically a different distribution, the t-distribution. Let's practice that one more time with a two-tailed test. I think I can squeeze it in here by looking at B. Let's look at B. Very similar. We have a sample of 16 again. We have a population mean of 0.47. We estimated the standard deviation as 4. We observed a sample mean of 0. We're testing two tails, same significance level. So we are setting up our hypotheses. Then the research hypothesis that we sort of want is that there's a difference from the original mean of 0.47 and the null hypothesis that there is no difference. This one is just different instead of an inequality because they say a two-tailed test is what we're doing. All right, so now we have our comparison distribution as before. It has mu m under the null hypothesis of 0.47 and an approximation to its standard deviation, which is why we use an S. The standard deviation approximation for the population of individuals, 4 over the root of the sample size, which is a very convenient 16, and we get a 1. Now again, we have an alpha of 5%. Let's visualize this again. Why not? Practice my drawings. Visualizing is very handy to help me remember the steps and understand what I'm doing rather than memorizing blindly. Understanding always beats memorization. So in the tail here, I'm okay with a 5% chance of rejecting incorrectly. That is going to give me a cutoff score according to my degrees of freedom and my alpha. So I look it up to get this t cutoff. In this case, a two-tailed test, so I did it wrong. I was testing you. Two-tailed test means in total, this is the positive, and the negative cutoff, I can make a mistake on either side. So the 5% has to be split up into 2.5% on either side. But it's just a rough drawing, so I'm not going to adjust my line, but it does move further out. So the table here is actually much simpler because they had to summarize it even further. I'm looking at the 15 row. I'm looking for two-tailed. I'm looking at 5%. I'm over here, 2.132 plus minus. 2.132 plus and 2.132 minus. So my t cutoff will be plus minus 2.132. Now I have to, based on my observed sample mean of 0, remember, we observed a sample mean of 0. Okay. What is the observed t-score? Just standardizing this using the formula here, formula there. As a reminder, you don't have to memorize many of these formulas. So the observed sample score minus the distribution mean over the distribution standard deviation of 1. Oh, that's super simple. That'll be just negative 0.47. So they sometimes give me nice numbers. Just save the calculator a little bit. But that is, oh, that's not very big in size, is it? That's unfortunate. I was hoping for something exciting. It is on the left here. Oh, it's far away from the cutoff. T observed is over here at negative 0.47. So we can say here, conclusion. Let's say here, since T observed is between plus minus T cutoff, we do not reject the null hypothesis as much as I hope to. I hope that this one would be different, but you know, the evidence is what it is. The evidence is not strong enough to suggest the well, we don't know what the story is here, to suggest the mean is different from 0.47. If I knew what the story was, I could talk about the effect of a treatment or whatever, right? But we don't know. Regardless of the story or lack thereof, we have the same steps to the hypothesis testing. So it is a very small adjustment that we have to make, but we are getting a little bit more realistic, I suppose, where we don't know the standard deviation and have to approximate it by way of the sample. Then we have a t-distribution, slightly different, but also not really that different in terms of how an answer is structured. All right. Hopefully that gives you some good examples to work from when you do your own problems. And we'll slowly continue with this t-test. We'll be here for a while, looking at a couple of different scenarios. All right, until next time.